Welcome back. Last time we have studied about solid state, their properties, types of different types of solids. Now we move towards next topic, that is space lattice or crystal lattice. Now, what do you mean by space lattice or crystal lattice? As you have seen, in a crystal, atoms are arranged in a ordered arrangement, because I told you last time that we studied only crystalline solids in this chapter. So, in a crystalline solids, different atoms are arranged in a regular arrangement. And when we show the representation, we represent all the atoms with the help of dots. And that arrangement of dots in space is known as crystal lattice. So, its definition is, it is a three-dimensional arrangement of atoms or points in a space or in a crystal. Suppose we have a crystal in which different atoms are present and they show regular arrangement, then their space lattice or crystal lattice can be represented in this way. This type of arrangement in a three dimension is known as space lattice or crystal lattice. And the points and these points which represents the atoms in a crystal, these are known as lattice points. So lattice points are the atoms or constituent particles which are represented with the help of dots within a space or crystal lattice. Now next is unit cell. Firstly, I tell you about unit cell in layman's language. Have you seen whenever we construct our houses, the basic unit is brick, and bricks, they are arranged one over other in every direction, either in x axis or y axis or z axis. Similarly, when we create a crystal lattice, then the smallest basic unit which are arranged in every direction or which repeated over all direction and form a complete crystal, they are known as unit cell. So, unit cell may be defined as the smallest portion of crystal lattice which, when repeated over and again in all directions, constitute a complete crystal. This can be shown as we have a crystal are lattice points. Which show regular arrangement. Then we draw the complete crystal like, firstly you draw a cube having atoms at the corners, then you draw atoms at the mid of every edge. After this, join the opposite midpoints. Now again you have midpoints like intersecting point of these lines. Join these also. Now you get here the intersecting point and these lines. So this is the structure of complete crystal in 3 dimensions. If you see here, this shaded portion, this is a unit cell. Why? Because when you repeat this type of unit along every direction, again, over and again, either you repeat it in x-axis, y-axis, z-axis, you get a complete crystal. So, unit cell is the smallest portion of crystal lattice which when repeated over and again in all directions constitute or form a complete crystal. I think it is clear to you now. Now next is types of unit cell. We have different types of unit cell on different bases. First classification is based on the arrangement of arrangement of atoms or constituent particles. Unit cell have been divided into 2 main classes, that is simple or primitive unit cell and non-primitive or centered unit cell. Now what do you mean by simple or primitive unit cell? Simple or primitive unit cell are those unit cells in which constituent particles or atoms are present only at corners. Only at corners. Whereas non-primitive or centered unit cell are those unit cells in which atoms or constituent particles are present at other positions in addition to corners. This is diagrammatically represented as, if we have a unit cell whose atoms are present only at corners. We know that a cube has how many corners? 8. So this type of cell, unit cell, is known as simple or primitive unit cell. Now, non-primitive or centered unit cell. As I have already told you that these are the cells in which atoms are present at other position besides corners. So these are further of different types, which I will divide into 2 types: simple unit cell, primitive unit cell. Now non-primitive unit cell is further divided into 3 types: face-centered unit cell, body-centered unit cell, and end-centered unit cell. Now what do you mean by face-centered unit cell? Face-centered unit cell is that cell in which atoms are present at corners as well as center of each face of a unit cell. As shown, if we have a unit cell in this case, atoms are present both at the corners as well as at the center of each face of a unit cell. And we know that in a cube there are total of 6 faces. 1, 2, 3, 4, 5 is front one and 6th one is which is behind you. So center of each face, the center of this face is somewhere like here, then this. Front face has center in this point and backward face has a center here. So 6 atoms at the center of faces and 8 at the corners. Now body-centered unit cell. In body-centered unit cell, atoms or constituent particles, they are present at the corners as well as at the body center of a unit cell. These are the atoms at corners. And what do you mean by body center? If you have a cube and you put a ball or atom inside it. That means that ball is at the center from each side. That is known as body center. Like this. This atom at the center is the center of every side. So this is body centered unit cell. Now next is end centered unit cell. Here atoms are present at corners as well as at the center of any two opposite sides or faces. So, in end-centered unit cell, atoms are present at the corners as well as at the center of any two opposite faces. Either you take these two faces or you take these two faces. So, this is end-centered unit cell. So, on the basis of arrangement of unit cell, we have total of 4 different types of unit cell. Simple unit cell, face-centered, body-centered and end-centered unit cell. Find out how many number of atoms are present within a unit cell. Calculation of number of atoms per unit cell. This is also known as rank of a cell. Many times in competitive exam, questions like what is the rank of a simple unit cell has been asked. So, rank of a unit cell is same as the number of atoms per unit cell. Firstly, we find out rank of a cell for simple unit cell. Rank of a simple unit cell. How can we calculate rank of a unit cell? As you have seen that in a simple unit cell, atoms are present only at corners. There are 8 corners, so 8 atoms are present. But in actual crystal, if you have seen this atom is like a sphere. And in this case, the whole part of sphere is not the part of a unit cell. It is shared by neighboring unit cell. I will show you with the help of this duster. Suppose you have this is the unit cell, suppose, and an atom is present at the corner like this. Atom is a sphere and it is present at the corner. So you observe that only this much part of sphere is shared by a single atom. Likewise, all other corners also has this much part of an sphere or atom. As a result, we can say that 1/8 part of this sphere is shared by this corner. Same 1/8, this one, and every atom shared only 1/8 part within a unit cell. As a result, rank of a simple unit cell can be calculated like there are 8 atoms at corner and each have contribution of 1 by 8. So it comes out to be 1. It means rank of a simple unit cell is 1. That means in a simple unit cell, if you merge all the 1 by 8 part present at each corner, they form single atom. Same is the case with other cells. So next is rank of a face-centered unit cell. In face-centered unit cell, you have seen that atoms are present at the corners as well as at the center of each faces. So there are 8 atoms at corners and each contribute 1 by 8 part, plus there are 6 atoms at face centers and each contribute 1 by 2. How? If you have a wall of a room and if there are 2 rooms in which common wall is present, and if you put some sphere in the center of that wall, that sphere is shared by both the rooms or both the unit cell. You can also observe this with the help of this duster. If we have here in the center there is a one ball between 2 dusters, then half ball is shared by this duster and half ball is shared by this duster. As a result, each atom has a contribution of 1 by 2. So rank of a face-centered unit cell is 8 at corners into its contribution and 6 at face center into its contribution, and this comes out to be 1 plus 3, that is 4. So rank of a face-centered unit cell is 4. Now third one is body-centered. Rank of a body-centered unit cell. Now we have seen that in the body center, atoms are present at the corners as well as within the body of the unit cell. And if we put a ball or a sphere within the cube, it is shared only by that unit cell. As a result, this has a contribution within the cell only. And rank can be calculated like 8 at corners multiplied by its contribution, that is 1 by 8, plus 1 at body center into its contribution is 1, because it is shared by only one unit cell. So it comes out to be 1 plus 1 equal to 2. So its rank or number of atoms within body centered unit cell is 2. Now fourth one is rank of an end-centered unit cell. Here we see that in the end-centered unit cell, atoms are present at the corners as well as at the center of 2 opposite faces. So its rank can be calculated like 8 at corners into 1 by 8 its contribution plus 2 at end centers into its contribution, that is 1 by 2, because it is similar like face center atom and each face center atom has contribution of 1 by 2. So it comes out to be 1 plus 1, that is 2. So Many times in competitive exam, question has been asked that how many atoms are present in a simple unit cell, or what is the rank of face-centered unit cell, like this. So you must learn that in a simple unit cell, number of atoms present is equal to 1. In a face-centered, it is 4, body-centered 2, and end-centered is also 2. So students, you have learned different classification of unit cell on the basis of arrangement of atoms within the unit cell. Before starting the second classification, that is on the basis of different parameters, firstly you must learn what do you meant by cell parameters. So our next topic is cell parameters. For differentiating or for measuring a particular unit cell, we have two cell parameters. One is axial length, which is represented by A, B, C, and another is axial angles, represented by alpha, beta, gamma. Now, what do you mean by axial length? If we have a simple unit cell like this, then suppose this is x-axis, y-axis and z-axis. The part of x-axis covered by a particular unit cell is this part. This is represented by, along x-axis it is represented by B, along z-axis it is represented by A, and along y-axis it is represented by C. Angle opposite to A, that is this one, is represented by alpha. Angle opposite to B, this one, is represented by beta, and angle opposite to C, this one, is represented by gamma. I will show this in a simplified way like this. If this is x-axis, y-axis, z-axis, then some part of this covered by unit cell, it is represented, this is A, this is B and C, and angle, this angle is alpha, then beta and gamma. So these are the different cell parameters. A, B, C are known as axial lengths, and alpha, beta, gamma is known as axial angles. Now, on the basis of these cell parameters, we have different types of. So second classification of unit cell is on the basis of cell parameters. Unit cells are of different types. This can be shown with the help of a table. So these are the 7 different unit cells, that is cubic, tetragonal, monoclinic, triclinic, hexagonal, rhombohedral or trigonal, and orthorhombic or rhombic. They have different axial lengths as well as axial angles. I will tell you a mnemonic for learning these 7 unit cells. But firstly, you see here in cubic unit cell, all the axial lengths A, B, C, they are of equal size. A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degree. All the angles are of 90 degree. And its example is NaCl and KCl. Second type is tetragonal. In this case, A and B, they are equal, but C is not equal. And alpha, beta, gamma, they are equal to 90 degree. Its common example is calcium sulfate, titanium dioxide. Then third is monoclinic. In this case, no axial length is equal. That is, A is not equal to B is not equal to C. They are of different lengths. And alpha equal to gamma equal to 90 degree, but it is not equal to beta. That means beta may be either less than 90 or more than 90. And its common example is monoclinic sulfur, sodium sulfate, decahydrate. Then triclinic. In this case, A is not equal to B is not equal to C. Similarly, axial angles, that is alpha, beta, gamma, they are not equal and they are not equal to 90 degree. They are either less than 90 degree or they are more than 90 degree. Its common example is potassium dichromate and pentahydrate copper sulfate, that is hydrated copper sulfate. Then we have hexagonal type where A equal to B but not equal to C. Alpha beta equal to 90 degree but gamma equal to 120 degree. And its common example is graphite, ice, HGS. Then we have sixth type, that is rhombohedral or trigonal, in which all the axial lengths they are equal and alpha, beta, gamma they are equal but they are not equal to 90 degree. Its common example is calcium carbonate and sodium nitrate. Then last example is orthorhombic or rhombic, where all the axial lengths they are not equal, that is A is not equal to B is not equal to C, and alpha, beta, gamma they are equal and they are equal to 90 degree. Its common example is rhombic sulfur, potassium nitrate, then potassium sulfate. Now, how do you learn this? There is a trick. If you see the first letter of all these, C, T, M, then T, H, R, O. Learn this table with the help of a mnemonic by taking the first letter of all these types of unit cell. CTM means contribute towards memory, and then throw, THRO, then throw it. You can learn this as this mnemonic. Then see here, in case of cubic, A equal to B equal to C, then these three you have to learn that here all the three are equal, here last one is not equal, and here both are not equal. Then repeat it in the reverse direction. A is not equal to B is not equal to C, then this one, and last one is the case where everyone is not equal to each other. Then you can learn these axial angles like first, second and last one, which I have written in black color pen. They are equal, in which all the angles are equal to 90 degree and they are equal to each other. And then these three you have to learn, green color pen, and this is the case triclinic where all are unequal and not equal to even 90 degree. An example you have to learn. Now one more thing, many times one more question has been asked in competitive exam, that is which type of unit cell according to cell parameter is the symmetrical, most symmetrical. So remember it, cubic unit cell. See here, A equal to B equal to C and alpha, beta, gamma all are equal. This is the most symmetrical unit cell. And triclinic unit cell is the most unsymmetrical unit cell. See here, triclinic. In this case, all the axial lengths as well as axial angles, they are not equal. So this is the most unsymmetrical unit cell and this is the most symmetrical unit cell. Now, one more thing. Till now you have studied two different types of unit cell on two different bases. One is on the basis of arrangement of atoms within the unit cell and other is on the basis of cell parameters. On first basis, that is on the basis of arrangement of atoms, unit cells are of four types: simple, then face centered, body centered and end centered. And on this basis we have 7 unit cell, which is sometimes also known as 7 crystal systems or 7 crystal habits. When you merge both the types, that is 4 types of unit cell, previous one, and 7 these types, we have number of arrangements, out of which practically only 14 arrangements have been exist, and that 14 arrangements are like this. Cubic show, these are arrangements, or you can also say Bravais lattice. Under cubic unit cell, atoms can be arranged in 3 ways. That is simple, face centered and body centered. In case of tetragonal, there are 2 arrangements, that is simple unit cell and body centered unit cell. Monoclinic also show 2 type of arrangement, simple and face centered. This triclinic, hexagonal, rhombohedral, these 3 types show 1-1 arrangement, and that is simple. In maximum of your books, it has been mentioned that hexagonal show simple arrangement, but actually in the higher class we studied that hexagonal show actually mixed type of arrangement, in which some atoms are present at the corners, some are present at the face center and some are present at the body center. So it shows, but it shows only one type of arrangement, that is one mixed, and this is simple. And last one, orthorhombic or rhombic, it shows 4 arrangements: simple, body centered, face centered and end centered. And when you add these, you will get 14. That means, otherwise when you merge both the classifications of unit cell, we have possibility of large number of arrangements, but actually practically when we observe, only these 14 arrangements of different unit cell have been observed, and these are known as Bravais lattice. That is why in many times it has been asked, how many crystal systems are known to us? So how many crystal systems? 7 crystal systems, or which is also known as crystal habits, and these crystal systems are same to that of these 7 unit cell. because the nature of unit cell, because I told you earlier that unit cell is a basic and fundamental unit of a crystal. So if a unit cell is of cubic nature, the whole crystal is also known as cubic crystal system. So we have 7 crystal system and we have 14 Bravais lattices. So this is all about different types of unit cells, different crystal system, Bravais lattices. Students, you must take screenshot of this table because in this table is very important. In competitive exam, this is very helpful. Thank you so much.